My title of my project is basically quantifying the feedbacks between pollution, radiation and meteorology, and my polluted megacity is Beijing. Although in theory this could work for other polluted megacities. So I'm going to quite quickly talk you through the pollution, how it interacts with radiation, what effect that has on meteorology, and then kind of what I've been up to so far. So first of all, as mentioned by quite a few people, we know air pollution is very bad for human health. 3 million premature deaths in 2012. It specifically affects more the elderly, children, pregnant women, and has linked to lots of different illnesses, so stroke, cardiovascular disease, diabetes. And the main focus, as Joshi said, is usually on particulates with a diameter of less than 2.5 micrometers, and that is because they're the particles that can actually get into your lungs, into your airways, and if they're small enough, diffuse through the alveoli and into the bloodstream. Okay, so air pollution in Beijing, as we've already heard, not very good, but it's not just because they've got very high emissions. They do have high emissions, but that's not all of the problem. So, no, I'm using this actually. So the meteorology, first of all. So you get very cold winters, very low wind speeds, and few precipitation events. Precipitation basically, I think as Joshi mentioned, will just wash out a lot of the particles from the air. So really good in terms of getting rid of air pollution. Wind speed, if you've got a lot of wind, it'll blow it out of the kind of city. You've got more kind of transportation. And the warmer, as I'll go on to in a minute, the warmer a place is, the more of this turbulence and this vertical mixing and these eddies that you get, which was spoke about in Joshi's talk. You've also got topography, so there's mountains to the north. You've got a lot of industry to the south, which means that if you've got wind coming from the south, where your industry is and your emissions are, they're going to get blown into Beijing. The pollution's then going to almost be trapped by these mountains from the north. And you can see in a lot of the measurement data that if you've got wind coming from the north, it's usually a very clean day. If you've got wind coming from the south, it's a really polluted day. So there's actual direct correlation between wind direction. You've also got emissions, so rapid industrialization, urbanization, and the use of coal, less so nowadays, but biomass burning as well. Okay, so I talked a bit about this feedback loop. The title of my work is about this feedback loop. So I'm going to try and explain it as simply as possible. So you've basically got a boundary layer which ranges in height, and it basically is the lower layer of the atmosphere where things are kind of trapped, and that ranges, it's usually higher in the daytime and lower at night time. So you want it to be higher because if it's higher, you've got more volume for your aerosols to mix in, or your pollution to mix in. So example of how a boundary layer might evolve over the day is you get your sunlight heating the surface then re-emits this radiation that it's got, warming up the surface air, which then mixes, hot air rises. So you get more mixing vertically in these kind of eddies, a lot more turbulence. However, when you've got pollution, what happens is the aerosols will scatter and absorb your radiation, so your surface is a lot cooler. You don't get the same kind of hot air at the surface, which then won't rise, and you won't get this kind of level of mixing. And so your boundary layer is lower, and when your boundary layer is lower, that means that your pollutants are trapped in this layer. This then means that because they're trapped, they're actually at higher concentrations, because they've got less volume to mix in, and that means that then loops back and creates a kind of positive feedback for this effect that you see, and we think it's quite important to sustain the haze. It's quite important in how long the haze might last in particular, so that's kind of what I'm trying to figure out. I'm trying to figure out how much of the haze longevity is due to this kind of interaction and this effect. So I'm using, this is just quick examples of how you can show that this effect actually does happen. So if the red line is your particulate matter concentrations, and your blue line is shortwave radiative flux, so the amount of shortwave radiation measured at the ground. Let me try and point. So you can see here when you've got this high kind of pollution, you've got this really low level of shortwave radiation. And then over here, you've got lower levels and you've got higher kind of peaks in your shortwave radiation. And similarly, you can measure stuff like the boundary layer height and the sensible heat fluxes versus PM1, just to show that this effect does happen. So I'm using this model. It's a large eddy model, which means that it directly resolves the eddies that Joshua was talking about, the big ones. So it means that I can really understand this kind of transport, this vertical mixing to a much higher resolution than other models, which tend to be more regional. So my resolution is quite small. I've also got this aerosol module, which can include all these aerosol radiation, aerosol cloud interactions. That's really important. Okay, so far, there's a lot of graphs on here, but so far, before I decided to look at this feedback effect, I needed to know, is my model working for a clean case in Beijing before I start putting in all these processes, because otherwise I don't know what effect is due to the pollution and what effect is just Beijing naturally. However, I came into some difficulties, as often happens in your PhD. So the main focus really is this graph to your left, this one here. Particularly if the straight line, not the dashed line, the straight line is your measurements, the dashed line is the model. So actually reproducibility isn't too bad most of the time, but then over here, in your lowest 100 meters, you're getting, this is potential temperature, you're getting a real discrepancy in the night time, so at 12 a.m., 8 p.m. Kind of time. And basically, this is a level of cooling which the model is predicting that isn't observed in the measurements. So there you go. So I started to think, why is this? The model itself, if you look at other kind of measurements for other places, isn't too ridiculous. But particularly for this case, it wasn't working. So I started to look at the urban heat island effect, because one of the main effects of this is that you get delayed nocturnal nighttime cooling. And basically the urban heat island effect is any kind of effect you get from changing your landscape to a city. So you can think about this in two ways. One of the things is the actual physical urbanization, so the changing from soil to concrete, and the actual buildings, the actual height of the buildings, which create a kind of urban canopy. But also you get heating coming from things like cars, actual heat coming from buildings, and actually even heat coming from the amount of people that you've got living in your city. So this can really be described through, like I said, through the two things, and this equates itself in the surface energy balance scheme with this QF and the delta QS, so the heat storage term and the anthropogenic heat flux. So I had to start including this in my model. So beforehand, in my model, you just have the net radiation, your sensible heat flux, your latent heat flux, and a bit of the QS, but it was based basically on a soil model, not a city. Okay, so I'm going to briefly just discuss this. Basically, it's just showing I've changed the QS, I've used these urban surface values and stuff like that. Still not getting the right answer. I added the QF, and if we just look really at the bottom part of the graph, you are seeing this evolution to get less and less cooling. So, in conclusion, I'm getting there. I'm not there yet. I'm hoping, I've spoken to someone that I think can help me with my problem. I've been working on this meteorology problem for about 8 months. I'm not a meteorologist. I really want to, get into the aerosols, but I'm still here, still staying positive. So this urban heat island effect is probably really important, and this kind of anthropogenic heat flux and the heat storage term, you need to probably include both of them, may have an impact in other large-scale pollution models. We'll see. And that's about it, I think. Oh yeah, and I've had some good times with the bad, so there you go.